Hello everybody! Today we have Artur Avila, the first Brazilian field medalist. Since getting this high prize, he has done many interviews, but today's interview is more philosophically focused and it's devoted to mathematical thinking. So it's about how Artur thinks mathematically. Artur, as I see, your strategy in solving problems is based on two main components. One is learning fundamentals and another is intuition. In one of the interviews you say, I would like to develop, you say, I often begin to work in an area, doing research even before studying the area, starting from nothing, without knowing anything. It's more important to have a very precise understanding of the fundamentals. So what exactly do you mean under fundamentals?
Don't know exactly in which context I said those things. If I would think about what I understand I was talking about, is it happens that you approach a new field that I'm not saying a field that's completely unrelated, but some place where ideas that I had considered before seem to be applied, some general ideas. A concept like renormalization or something like this, a broad concept that might be applied in different ways in many different types of situations, or several kinds of probabilistic arguments or so on. So then at this moment you have some kind of specific field that you can approach, where you can, which sometimes are like what has happened in practice is that sometimes there were kind of famous problems that were that were resisting attacks, and the actual content of the theory was not enough to like the way people were proceeding along the theory was not leading to the solution of this problem. So sometimes it depends on bringing kind of completely simple ideas that don't need so much theory, but look at some particular features of the problem that sometimes are much more basic than the whole extent that people are developing. So in a few situations that this happened, I took some specific problem, I isolated very few parts of what was necessary to understand it, and attacked it with general ideas and intuitions that permeate the whole of dynamical systems, because you have several parts of dynamical systems that sometimes are not talking to each other, but there is some kind of general ideas that you can try to apply in different contexts. So I think that I was talking more or less about this kind of way that you can approach hard problems when getting into a new field.
Can you give an example, more or less accessible?
Accessible is kind of hard. One of the examples that happened was the problem of weak mixing for interval exchange transformations. It was in a well-developed field. So you had simple transformations for which they are related to tight Miller flow and things like this, so that it was very much studied from several points of view. And there was this basic problem about the dynamics, which was to establish that typically the transformation were either kind of rotations or typically had the weak mixing property. And this was resisting several attacks by groups. And at the moment that I started working on this, I knew very little about the whole theory of interval exchange transformations. Mm-hmm. But I extracted just the fact that there was a renormalization operator with some hyperbolistic features that were available. So there were some kind of recent results about how this renormalization operator behaved. And there was a general approach of applying some direct parameter exclusion, so concentrating much more on the analysis of parameter space than in the understanding of phase space. So that was the idea that I decided to follow with my co-author. And we got relatively quickly to the solution. So we needed very little of the theory. We needed some kind of important piece of the theory, but then it worked from kind of general dynamical reasons within there was some kind of strong technical result that was necessary, but it reduced entirely to an analysis basically of probability. So it was not something specific about those interval exchange transformations, but then a problem in parameter space that became a problem in essentially probability.
Mm-hmm. Okay, thank you. And you also say that solving problems from scratch involves a bit of technical characteristic of the person and their intuition too. So what do you mean on the technical characteristics of the person? Learning, knowing fundamentals? And what do you mean on the intuition?
Well, you need to kind of intuition is usually something that confounds with like difficult to classify. Normally, if you think a posteriori, it comes from experience. So you can kind of connect what you're trying to do with situations where you understand more or less what has worked and what does not work. So that you need to make the right analogies to see to which extent and to, with which theories you should compare that it should kind of apply in more or less similar situations that to what you're doing. So you need to kind of make some educated guesses on this, and you can kind of use this to rule out some approach to the problem as well. So you can kind of, with intuition, you decide to eliminate, like, of course, when you start a problem, there are a large amount of ways that you could approach it, and it's good to be able to eliminate quickly things that are not very promising. So you expect that if you follow a certain route, you are going to face certain difficulties at some point. So you eliminate some ways, and what's left is the way that you may kind of try a little bit harder. So all those kind of aspects of the person, the experience and so on, led them to be kind of in a better position to go for certain problems or not. I understand. But.
Okay, thank you. And in your intuitive thinking, you said you use associations, comparisons. How about visualizations? Some people claim that visualization can provide us with prior access to information, to grasp some patterns in chaos, for example. What is your experience in using visual perception and visual imagery? Do you use drawings on paper?
I think that visualization, as understood by mathematicians, particularly certainly by me, is something more than something just purely visual. Like it's just some kind of something non-verbal that, like, the mathematician thinks about the objects in a way, like the brain works, and it's difficult to tell exactly. And there are some ways of understanding that are not kind of, that do not translate simply to a sequence of statements. And that would be a verbalization that happens when you write a paper or something. So what is not of this kind is just kind of, it could be imagined pictures in your head, but I think that there's more than that. Like what we can imagine as calling visualization is all kinds of ways that your brain is processing the information that it does not translate directly to something verbalizable. Like it is seeing things. You use the word seeing, but maybe it's not accurate to say that it's just an optical representation. It could be, I don't think it reduced to this. There is a component that's optical. We imagine things moving around and so on, but I think there's more than that. So I think that a large part of, which is one way that I think sometimes that one obstacle, one characteristic that the verb, the way that people communicate in the end, and the proofs and so on, the language that we use is a way that mathematicians translate their actual way of thinking. So each person has their own internal models that are not kind of, you cannot draw often, and you cannot kind of, cannot be described directly of how you think about things. And then there is a mental process of translating that, and then the communication between the mathematicians use the actual rules, but your actual brain doesn't process the things in this way. But I don't know how to describe. Like for me, it's like a little, I know that I'm kind of doing this translation, and I know what's going on. And then I need to translate to a language, and then I can communicate to someone. And I imagine the other person is doing the same. So it's it should be much better if you could send immediately how your brain works to the other person, but this is not possible.
But do you use drawings?
I rarely take paper and do drawings. I usually think just within my head. So.
And if you need to explain somebody the
I
idea.
make drawings, but my drawings are very abstract. I don't try to make them least realistic. They are usually some kind of just conceptual drawings. The actual realism of or accuracy is not very important, more like pinpointing what seems to be the important thing. So a drawing can quickly convey that this is something important, and it's not kind of that it's an accurate representation of the actual geometry, but rather the concept that's going on.
Okay, interesting. And now about experimenting. In your words, what trips research up is having to go outside established methods, discover something, and try to identify a way to attack the problem. My question is, what is your experimenting with the objects you are dealing when going to beyond prescribed rules?
Normally, you're going just a little bit beyond of what is. That's the normal. Like you need to, when you are within a problem, either you have a very good idea of what you should do, and then those problems, they are not kind of very challenging and interesting. But usually, a problem that you are going to attack, it doesn't yield immediately to just kind of applying the what everybody knows that could be applied. Usually this will depend, to get something interesting, is to have an extra idea that people are not taking into consideration. That's so you need to identify normally what is so the problem usually breaks into there's a lot of things that go, and you can try to understand what kind of comes down to just kind of a routine work, which can be very technical and very difficult still, but which you could classify still as routine, and where the routine arguments will break down, and then you isolate where's the point that needs to be that need care, and you need an idea. And then you hope to have an idea, but then this can come from kind of bringing it from somewhere else, or just kind of at some point you just have some kind of fantastic breakthrough. But this is like you imagine some new thing from nothing, but this is extremely rare. But in some ways there will be some problem that escapes techniques. Otherwise, someone else would have done. It is. It's this that needs to be identified, and then you. Sometimes there's no recipe to kind of solving this part of the difficulty. It's kind of, you can try several different ways. There is the kind of obsessive way that you try everything that's in front of you until which if you're desperate and you think that you're just kind of missing this, you can try, and then but this is usually frustrating. Another way that often works is that you're not actually you understand and you are aware that there is this big difficulty, and you don't have an idea, and then you work around it on similar problems where you kind of develop your understanding, you expose yourself to other ideas, and then you need to be ready to recognize that while you are studying something else, maybe something that you discover in this different context can be applied exactly for that particular step. So this happens more often, that you just happen to by chance to identify some new technique. And then the important thing is to recognize that then you can apply it in that exact context that that you're blocked.
Have you ever invented some new techniques?
Everything kind of to one. There are a lot of mathematical ideas. So even a posteriori, something that you discover could be traced back to some extent to some. It's connected to other things, because right now the knowledge is very. I certainly. Discovered new things that are kind of how new you have to understand depends on how it can be identified, but it was not immediately in that context was not it's just not existent, and it was certainly original in that situation. So this has happened a few times, yes. Sometimes very simple concepts, the ones that are most powerful and that leads to most. It starts with a very simple idea that discovers a new thing, and then what comes is that to identify that this is very important. It happened once that I discovered something that and proved some very simple fact. The proof was used some technique, but it was a surprising fact. Which understood and obtained that some number that could be defined was always an integer. That was discovered. It was a priori a real number, but it turns out to be an integer. And then I was aware of that and understood a few repercussions, and I had no idea that that this would be so useful. It took me years at least 2 years, to just kind of one day just thinking, I see that this number was so important, just this fact that this number was an integer, but I didn't realize, so I could have realized immediately, oh, it's great that numbers, I didn't know that I should explore this fact more. And then at some point you realize, once you realize that this is really a new fact that is important, so you hope to realize that, then you bring in everything that you have, and now you have one extra two. One extra two by itself is not, doesn't lead to much, but one extra two plus everything else you know sometimes leads you very far.
All right, very interesting. So you work with analysis, statistics, geometry, and these all contribute to dynamic systems, right? How would you characterize specifics of thinking in these disciplines, and how these types of thinking fuse into dynamic systems thinking? So statistics, analysis, statistics, geometry, and dynamic systems.
They are so kind of, they go together so much, they are kind of just part of several ways of looking at same things sometimes. Like there is something that's more probabilistic thinking, of course, but probability comes with analysis, and the understanding of the geometric shapes in the end will need both of them. Sometimes the geometry guides the analysis, so they are all together in the end. You could isolate immediately. You can have ideas that are formulated very much in a geometric setting, or very much in a purely probabilistic setting, or completely in a probabilistic analysis. Once you have all of them, you can also think of them together, and then they don't make in those contexts they don't exist by themselves. They are all together. It is a kind of analysis that's guided by geometry. It's a kind of probability that's guided by whatever. So they exist together with more kind of proeminence of one or the other, but they are all together. What I find it more difficult to put together with the others is the part that I'm not specialist. It's kind of algebra, really. So algebra for me is more mysterious. I don't think of it as connected. It comes with a different. It's a different input altogether. But those other three things, they kind of exist together, and then you can have more emphasis on one or the other, but they are parts of a same body.
Would you agree that algebra is more like combinatorial type of science?
Combinatorics also interacts a lot with analysis. Algebra. What I think usually is that there are aspects that are very exact, and then there are precise identities in algebra that come from you deduce things through series of identities. Often this kind of things is very far from the way I think, which is more of trying to do inequalities and estimate what's larger and what's small, and then this is what's guiding. So your picture of what you're trying to see is not something saying that this is exactly equals that, but that something is much bigger than something else, and then you can neglect something and not something else, and so on. So this is a really different type of thinking.
Interesting. You said I have changed sub-areas several times, and each time I solved an important problem right away, and only later understood what the theory said about that problem. Did this require changing the type of thinking in your head? For example, geometrical versus, algebraic thinking, and only after does it mean that you learn this sub-area formalism because you need to wrap up your intuitional idea?
So I was talking about specific incidents, so that it's not a recipe. It's what happened a few times with me. Is that I was convinced to work on some problem that looked interesting, and then looked challenging, and appeared like something that could be like the problem about weak mixing of interactions transformations. It makes sense for a dynamicist that doesn't know much about the theory. And I was convinced that it was a natural problem to work, and then I did this, and but then you start, like in those cases, you start to get I got interest on the problem from outside, and then you get more intimate with the objects that you're dealing with, and you get more curious to understand better them. I understood one aspect of those objects, but I got familiar with them, and I liked them, and I wanted to know more about them. And then I see that there is a whole theory more. And then I was very interested in the theory because it was talking about things that I was already interested in. So it was easier to kind of get interest in this theory because I liked what it was talking about already. So that was how this connection happened. I first liked this, and then I didn't know my theory. I thought it was very complicated, but then I worked there. I get happy about that, and I get so connected that I want to know more. And then I get into the theory, and then there is much more complexity that comes in, and then I can start working on problems that involve this extra complexity that involves much more theory. So that's basically what this happened a few times with me on some fields like the Schrödinger operators or with this problem of interaction transformation. That's what I was talking about in those cases.
But okay, when you change this sub-area, do you really need to twist your mind somehow and start thinking in a different way, or is it more?
Initially, at this initial approach, before you get to the theory, in the problem of solving a problem, you're usually close to your. So I approached it from my general thinking. Like when it worked fastest, because it was approachable from kind of an understanding. So it was more kind of looking at something that was considered too special, and then thinking of this from a larger point of view, and using kind of from a viewpoint of more a larger dynamical viewpoint. So that was what I meant. And then as you get in the theory, then you kind of you add to you a lot of different ideas, and really you're going to be exposed to some things that you could not have proceeded but just by in this way that you did for that specific problem. And then you can learn more geometry and so on, but it goes in this in this sequence of stages.
Right, thank you. Now we are approaching a question of mathematical beauty. You said that you choose a problem which looks beautiful for you. That's the way you choose the problem to attack. So, and typically beauty, mathematicians usually say, is simplicity, generality, and surprise. What is beauty for you, mathematical beauty for you?
Depends. There are, of course, statements that they work so nicely together, and then there are some analogies that in dictionaries, and then there is this kind of connections between things that seem so far apart, and then suddenly, so there is this kind of things that people think that are beautiful, right? So you have a whole theory built on some foundations, and another theory built on some foundations, and then you discover that somehow they're talking, and there is a correspondence between them, and this correspondence is generally acknowledged as beautiful. There is some kind of it's difficult to say. It's an aesthetic beauty, but I would connect also to some kind of pleasure that you have on working on some things that sometimes I wouldn't describe as arising from beauty, but some ways of working, technical ways of working, for instance in analysis and so on. When you put together some interesting estimate or something like this in a very convoluted way, but with some kind of guiding principles, and then in the end everything works out, and then this I have compared with like a kind of pleasure that people have when they do some artisanate, like they are dealing with some kind of very concrete objects which have very specific rules, like when you deal with a real thing, then you are bound to laws of physics and so on, then only so much that you can do, but there is a lot of flexibility as well, and there is a lot of pleasure to put your hands on that, so that you make your hands are dirty. It's not at all this kind of aesthetic beauty, but there is also a pleasure of putting of working directly with your hands on that, and then some aspects of analysis feel like that, and then when you are doing this work it can be pleasurable as well, even if it doesn't correspond to the usual notion of beauty that people usually are referring here, like which is kind of more kind of clean and very perfect picture that emerges after everything goes together and so on.
So it can be something.
It can come from different aspects. Of course, it's beautiful when you have something like that can be thing that you define things, and then the theorem is just whatever is an integer. That's certainly a beautiful result that you get. Something that arises suddenly an integer is, of course, a beautiful statement, and there is no doubt about that. And the proof is actually simple of that statement. But then there is something more complicated. It's far from having such a simple statement, but the proof actually brings you a lot of pleasure in the process.
Mm-hmm. But is it really beautiful or simply interesting?
Like a statement that is so simple, I don't think you would call it like. Of course, it's also it has it is immediately something that reveals a lot. So the interesting is that it reveals a lot about that. It could be a characteristic that's kind of perfect, but doesn't lead much anywhere. So that it should be just beautiful. Perhaps it could there could be something like this. That's a dead end, but still a beautiful dead end. But on the other hand, it could be kind of just a fundamental property that's necessary for better understanding of this, because you're generally interested in understanding several aspects of whatever is the object that you're dealing with, and deeper understanding relies on several things. Some can be not beautiful but essential. Some can be beautiful and essential, and things like this. In this case, I'm coming to an example. This turns out to be a fundamental feature. Like there was a difference between when I discovered that something was an integer and just looked at like a very nice, but I didn't understand how important it was. I didn't understand it was fundamental. Later on, it was clarified that it was fundamental, so that you cannot understand this without having realized that.
And when you understood this, did it appear more beautiful for you than it used to be before?
The whole connections that arose after, like what emerged of this, was kind of more complete. That thing, that just statement about integrality, was become just a component, and then there was a whole thing that comes out that has many nice aspects and other that are artisanal and so on. So there's a whole bunch of math that issued from that.
And then it became really beautiful.
It's something that I like a lot, certainly.
Okay. We can distinguish beauty of a problem, of a solution or a proof, a mathematical object, and also a representation of mathematical object, which can be a mathematical construction or it can be a visualization, for example.
Mm-hmm.
You know, in dynamic systems you have beautiful visualizations, sometimes computer visualizations. Mm-hmm. So the pleasure of beauty inspires you, but also may have a stronger roles, for example, belief guiding or even truth guiding, as some people think. Have you ever been well led to some idea or have been misled by beauty in choosing a problem first?
Well, when you choose a problem, or maybe you choose which direction to go in the problem, it's you maybe kind of get misled. Yes, you kind of may choose wrongly, because it's like what's to choose wrong problem is depends in which context you imagine. You can imagine that you're choosing a problem that's just kind of impossible. That's kind of a bad choice of a problem. Like it's impossible to solve at the moment, for instance, at least, and it can. Things look like it should lead in this way, and then you should go for this kind of theorem, and in the end this theorem is just not going to be available, and there's nothing that you replace. So that's certainly something that does happen.
But in your experience, did it happen to you that beauty led you to a very amazing problem, and
to lead you to a good problem that in the end didn't work? It's difficult to say that. I think that maybe I just gave up too soon. I know that for proofs it is definitely. Again on the same topic that I was discussing. There was a beautiful proof that had all the right, that should be looked for, because that was clearly the correct proof that should be obtained, because it would be very natural, and it had all that was the guiding principle in the end, and you just need to solve some technical aspects and everything would come together, and then it was just impossible to do it in this way. And then I never managed, and then it seemed extremely hard. The picture looks extremely nice until you look at some specific technical detail. It can be easily explained and so on. It just doesn't work as it should. And in practice, it is replaced, the whole beautiful thing, by something very ugly, but that works. There's nothing looks like it's going anywhere, and then like one proof, it kind of is clear what's going on, and that never works, and the other one doesn't seem that's going anywhere, and then leads you to the solution. So I had to replace the beautiful proof that doesn't work by something that works and just ugly. But in the end, the result is beautiful, so that's okay. The result is easy to state. The problem is the proof is complete catastrophe.
Mm-hmm. how about visual representations, beautiful visual representations?
Of course, I work with some beautiful fractals, but I kind of I don't go too seriously in exploring those obstacles. They kind of motivate at some primitive level, and then quickly they are replaced by the math that's behind, and then I never come back to the looking at the I usually only use the picture to show to people, but in the end I never thinking of those pictures.
Mm-hmm.
Like I know they exist, but.
Do you think they reflect some abstract beauty?
It is aesthetically, certainly yes, but this just doesn't help at all to do the math, so I'm not concerned during doing. In my thinking, I'm not concerned. It's pleasant to look at, but and I like the pictures, but it doesn't have to do with my math very little, except to say, well, it's nice fractal, maybe I work on this, but then I never come back to looking at them, like as a mathematician.
Mm-hmm. Okay, it seems that your motivations are the pleasure of beauty in choosing a problem for startup, then finding a beauty in discovering a solution, maybe also, yeah, and an intuition later when you are trying to attack the problem, which probably is also kind of feeling of that something is right, something connects well, something is fitting well, yeah, feeling of fitting. And finally, you are wrapping up your intuition, your idea you found in mathematical terms, yeah. So you have to teach yourself the new technicality in order to write down the formalism, right? So you have to teach yourself these technicalities, and then you find the pleasure of achievement. Do you?
When you manage to put everything together,
yeah,
and that solve the problem, yes.
Like you're saying that you already solved the problem. Now you just need to write it down mathematically, right?
That's not very pleasant usually. I don't like very much this part. The pleasure comes when you understood, and then the writing up is kind of the bookkeeping, and is usually sometimes you can be surprised, and then that's kind of not very nice. But I'm not very attracted by the. I don't like particularly this part. Like it's a lot of. Well, you either do it well, and then it's extremely tiresome. It can be. It's sometimes an exercise in writing. And you can try to write beautifully and actually have a lot of pleasure with the text that you produce. It can happen, but this is so much work that it just takes so much time to write a beautiful mathematical text. And I can do I think good work, but taking a lot of effort to do that. I prefer the other aspects that come before that.
So what is your greatest pleasure in doing mathematics?
Like the parts that like there are the moments where the biggest pleasures, and the moments where you realize that you have a new tool and a new idea that can be applied in some situation, and you're exploring the consequence. It's usually a very exciting moment that doesn't happen all the time, but that you have something new and you're trying to connect to things and you feel that you're going somewhere. So that's the kind of best moment.
That's great. Again, you said somewhere that in collaboration with your colleagues, first you learn fundamentals, right? And then also you talk to people when you already have solved the problem. You learn some exact details about the sub-area, yes, about the problem. Talking to experts. So it must be very precise, pinpointed collaboration, right? But why can't you read? Why do you saying you prefer talking to people rather than reading publications?
When you talk to people, they can quickly direct you to what's actually essential to the understanding. A paper usually contains a lot of things that are necessary so that things are correct. and they're formal, and they come from one point and get to the end. But when you talk to someone, if you have a good communication with them, you can isolate what is really, where things are happening and where things are just kind of doing routine work. So it's very important to kind of not get bored to hell with what you are studying, to kind of understanding what's important and where things are actually happening. And this you get much more quickly just by talking to someone that understands very well the subject. They can isolate now. Here is what's going on in this paper. Usually maybe there is just a single idea. There's a paper that there is 30 pages, and then there is one point here that if you know this, then you can fill up the other 30 pages, but you are not going to do it, but you could do it. So the guy, instead of having to kind of do 30 pages, it tells you one idea, well explained, and why it's so important. So it's kind of much more efficient way of actually to that in your mind you are going to have just the essentials, and you knowing that you can connect the essentials with using your standard techniques.
And is it always better in person rather than by email? Or?
It can work pretty well by chat, like not by email, that's a little bit too slow, but if you use any kind of instant messaging, I find that you can send ideas in one and other way. So typically you send ideas one to each other, and then there is a moment where things maybe happen, and then you're stuck and people have to think by themselves. It takes a few days that people are thinking, then they come back and discuss the ideas and maybe it unblocks. And it's very useful also to talk to people, because as I said, there is a process that you're communicating where you're translating your mental image of the objects to the mathematical language so the other person can understand. And at this moment, sometimes you understand things. The moment that you tell things to people is a moment that you also understand something yourself, usually. So the communication is important also, to explicit communication is important as well.
Now, how do you see a bigger picture of today's mathematics from your perspective? What is today's mathematics like? What are the main flow, what mainstream core fundamental areas today?
That's kind of very vast, and I wouldn't dare to kind of discuss fields that are not my own. I know that there are several advanced in fields that are far from dynamics. In dynamics, there is a lot going on in the theory of more rigid dynamics. So that's which a part of this was includes Tait-Miller theory and so on. So that less flexible objects. So that and that often will be connected with some kind of more algebraic ideas and structures. So this has kind of and connections to sometimes number theory and so on. So this has kind of advanced a lot in recent years. And with respect to other parts of dynamics, it's difficult to. There is like in one-dimensional dynamics, that's the field that I started. There was a lot of advance that have been going on, and still. Feel that something's missing, and it's difficult to know whether we are close or not that close at this moment to solving some questions that are kind of very that we've been trying to solve for decades. So I can tell, like, this is something that I would hope that we'll keep having some kind of strong, but it's kind of a little bit isolated. I understand that one-dimensional dynamics it involves a lot of specific knowledge that is very difficult to communicate to the broader community, and then there are other parts of dynamics that are much more intercommunicated with other aspects, but in this way, I think that this is algebraic clearly something that's being studied a lot recently.
And how about the future discoveries, developments? What would you anticipate in the nearest future?
I think it's very difficult to anticipate, because to anticipate usually you need to be very close to knowing, and it's almost like you are anticipating just what you actually know how to do it. So usually I find it very difficult to predict what I'm going to be working on in a few years, or what will be the direction that I prefer to be kind of following than kind of trying to be prophet here.
Okay. And finally, the actor studio question. If you met someone who knows everything, like God, What 2 questions would you ask him?
I probably don't like. Probably not mathematical questions. It needs to be mathematical questions.
Kind of science related.
I probably wouldn't waste my questions with mathematics, but if I would ask mathematical questions, I think I know the. I would like to. Though I would like to know the, but not just a yes or no question. Like he need to show the proof of that the Mandelbrot set's locally connected. It would be nice to have that, and probably it would be nice to see a proof of the Riemann hypothesis as well. But I want the proof, not the yes or no question. And if I can have to ask that, but probably I wouldn't waste this opportunity with mathematical questions.
But if it's only yes or no question?
Yes or no question. So just know whether something is true or not. Then I would have to reduce to something that I actually don't think I know, would guess the answer. I don't have a candidate. I would probably give a suboptimal answer here because I have some things that I'm curious about, but probably this would be a waste as well. I would kind of need to prepare a lot before wasting my questions on some specific yes or no question.
Right. Thank you so much.
Thank you.
Thank you. It was great.
Okay.